So imagine you are just holding a rock in the palm of your hand, just a normal, heavy, dull gray stone.
Yeah, the kind that doesn't really look like much, just sits there,
Yeah.
completely unassuming.
Right, exactly. You could toss it in a pond, skip it across the water. I mean, it feels completely ordinary.
But it's not.
No, it's really not, because what if I told you that inside that one little rock, there is a sleeping giant?
A very, very powerful giant.
Right. That, buried within its atomic structure, is enough energy to light up an entire city. That a handful of these stones could completely replace a mountain of coal, literally millions of tons of it.
It sounds like science fiction, honestly.
It really does.
Uh,
But today, we are going to find out exactly how to wake that giant up. Welcome to our deep dive.
Glad to be here. We got a fascinating source text today, a comprehensive engineering chapter that breaks down the whole process.
Yeah, we are going from the foundational physics all the way to the Manhattan Project. Our mission today is to pull apart the mind-bending reality of nuclear power. To understand how a dull gray rock can power a modern metropolis, we actually have to look at a fundamental glitch in the universe's math.
It really is a glitch, and it's one of the most profound discoveries in human history. To find it, we have to go back to 1907.
Oh, to Albert Einstein.
Exactly. Albert Einstein and an equation you have almost certainly heard of. E equals mc squared, energy equals mass times the speed of light squared.
Right, probably the most famous equation in the world.
Oh, definitely. And what it fundamentally states is that mass and energy are not two entirely different things. They are just two faces of the exact same coin. Like they can convert into one another.
Okay, but how does that actually play out in the physical world? I mean, my coffee mug has mass, but it's not turning into pure energy.
Well, our source text provides a really fantastic concrete example of how this works at the atomic level. It's what we could call the helium math problem.
The helium Okay.
Yeah. So if you look at a helium nucleus, it is essentially made up of four building blocks. You've got two protons and two neutrons.
Okay, so 4 individual pieces.
Right. Now, physicists know the exact weight of those individual pieces. A single isolated proton weighs 1.00073 atomic mass units.
Tiny.
Incredibly tiny. And a single neutron is slightly heavier at 1.00087. So if you do the math and add up the individual weights of two protons and two neutrons, you get a total expected weight of 4.0320.
Okay, but I'm guessing since you called it a math glitch, the scale tells a completely different story.
Exactly. When you actually weigh a fully assembled helium nucleus, it doesn't weigh 4.0320. It weighs 4.0015.
Okay, let's unpack this for a second. Imagine you are baking a cake. You carefully weigh out your flour, your sugar, your eggs.
Standard ingredients, right?
Yeah, you put exactly 2 pounds of ingredients into the mixing bowl, you put it in the oven, but when the baked cake comes out, it only weighs 1.9 pounds.
Which makes no sense.
None at all. Where did the rest of the cake go? The math doesn't add up. In the case of the helium atom, there is a mass defect of 0.0305 atomic mass units. That weight is just missing.
What's fascinating here is what happens to that missing weight. I mean, it doesn't just vanish into a void. It becomes what physicists call binding energy.
Binding energy.
Yeah. When those protons and neutrons fuse together to form the nucleus, a tiny fraction of their actual physical mass is converted into the energy that permanently holds the atom together. It's like the cosmic glue.
Wow. And because of Einstein's equation, we know that if you can reverse that process, if you can somehow break that glue, that tiny bit of mass turns back into pure, raw energy.
Exactly. And they didn't just guess this. They proved it.
Wait, really? Did scientists actually prove this without just, doing the math on a chalkboard?
They did, and it was a monumental moment. In 1932, two scientists, Cockcroft and Walden, set up an experiment where they fired high-speed protons at lithium atoms.
Oh, so they just blasted them.
Pretty much.
Yeah.
They essentially forced a nuclear reaction to happen in the lab. When they measured the results, they found the exact same mass defect. And, crucially, they detected a massive release of kinetic energy that perfectly matched Einstein's equation.
So the missing mass had literally transformed into a burst of energy.
Yes, the theory was real. E equals mc squared wasn't just math anymore.
Okay, so if we know that breaking the atomic glue releases energy, how do we actually force that mass to go missing on a scale large enough to, boil water and generate electricity for millions of people?
Well, that requires moving from these individual particle experiments to a massive, sustained chain reaction. We call this process nuclear fission.
Fission, right, splitting the atom.
Exactly. It involves splitting a heavy, unstable atom. And the atom of choice for this is a very specific isotope of uranium called uranium-235.
How exactly do you split an atom, though? I mean, you can't just take a microscopic hammer to it.
No, you shoot another particle at it,
Hmm.
you take a free neutron, and you fire it directly at the nucleus of a uranium-235 atom.
Oh.
When that neutron strikes the nucleus and gets absorbed, the uranium atom becomes incredibly unstable. It jiggles, it deforms, and then violently splits into two completely different lighter elements, often things like krypton and barium.
Wait, if we are trying to crack this nucleus open, shouldn't we be smashing that neutron into it as hard and as fast as possible?
Counterintuitively, no. In quantum mechanics, if the neutron is moving too fast, it will actually just zip right past. Or it'll bounce off the uranium-235 nucleus without being absorbed at all.
Oh, so think of it like playing miniature golf. If you hit the ball way too hard, it will just skip right over the cup, even if your aim is dead center.
That is the perfect way to visualize it, yes.
The neutron has to be moving slowly enough for the nucleus's gravity-like forces to actually, catch it and let it drop in?
Right. It has to be a slow-moving neutron.
Mm.
But the most crucial part of this process isn't just the splitting of that single atom.
What happens next?
When the uranium atom breaks apart, two massive things happen. First, it releases 2 or 3 brand new free neutrons, which go flying off to hit other uranium atoms.
Oh, so those split, releasing more neutrons, which hit more atoms. That is your chain reaction.
Exactly. But second, and most importantly, that split releases 200 million electron volts of energy.
200 million electron volts per atom. Let's translate that scale for you, the listener, because the numbers in the source text are incredibly difficult to wrap your head around.
They really are staggering.
If you take just 1 single gram of mass, so roughly the weight of a standard paper clip, and convert it entirely into energy through this process, you get 25 million kilowatt hours of power.
To put that in perspective,
Yeah.
to squeeze that same amount of energy out of the ground using traditional methods, you would have to burn 5,000 tons of coal.
Wow.
Yeah, for 1 single gram of converted mass.
The source material gives another crazy logistical comparison. Think about a massive 1,000 megawatt power plant running on fossil fuels.
Okay, a big one.
Yeah. To keep the lights on for a year, that plant needs about 3 million tons of coal to operate. That is an endless line of train cars chugging into the facility day and night.
Just constantly feeding the furnace.
Exactly. But a nuclear plant of the exact same size, it requires about 18 to 30 tons of lightly enriched uranium for the entire year.
That's nothing in comparison.
Right. That means the reactor is literally consuming only about 2 kilograms of uranium-235 a day. You could comfortably carry a day's worth of city-powering fuel in a backpack.
It fundamentally rewrites our relationship with fuel and supply chains. You no longer need to continuously feed a sprawling, dirty furnace. You just need a few dense, heavy rocks.
There is actually a really beautiful metaphor highlighted in the engineering text. It references a verse from the Quran that marvels at the idea of stones being used as the fuel for a great fire.
That is striking.
The authors of the text point out how remarkably prophetic that imagery feels today. Because when you strip away the steel and the concrete, that is literally what a nuclear reactor is, a furnace that burns stones.
And it's an incredibly clean fire, relatively speaking.
Here's where it gets really interesting. If you look at the environmental impact noted in our sources, a traditional coal plant emits about 700 grams of carbon dioxide for every single kilowatt hour of electricity it generates.
Which adds up incredibly fast.
Right. But a nuclear plant, it emits essentially zero.
Wow, literally zero.
The source puts it at around 3 milligrams, and that tiny amount is just from the life cycle of building the plant and mining, not the fission itself. The actual splitting of the atom produces absolutely zero greenhouse gases. It is just pure, intense heat.
But of course, getting that fuel ready to burn is one of the most difficult, painstaking engineering challenges on the planet.
Right, because if these rocks are so incredibly efficient, why aren't we just digging chunks of raw uranium out of the side of a mountain and throwing them directly into a reactor? Like, what's the catch?
The catch is that the specific type of uranium we need, that uranium-235, is hiding in plain sight. When you mine natural uranium from the Earth, 99.3% of it is a completely different isotope called uranium-238.
And U-238 doesn't work for a chain reaction.
No, it actually ruins it.
Wait, ruins it how?
U-238 is prone to absorbing those free-flying neutrons without splitting. It acts like wet wood in a campfire. It suffocates the reaction.
Oh, I see.
Only that tiny 0.7% is the fissile U-235 we actually want.
Okay.
So to make nuclear fuel, we have to enrich it. We have to artificially increase the ratio of U-235 to U-238.
But if they are both uranium, how do you separate them? Aren't they chemically identical?
They are completely chemically identical. They react to other chemicals in the exact same way. You can't just pour an acid over them to dissolve one and leave the other behind.
So what do you do?
Well, the only physical difference between them is that U-238 has 3 more neutrons, making it incredibly, infinitesimally heavier.
I was trying to think of how to explain how ridiculously hard this is. It's like having a giant sandbox filled with millions of grains of sand,
Okay.
and someone tells you to pick out only the grains that are a fraction of a percent lighter than the rest. And you have to do it wearing a blindfold. You just have to feel the microscopic difference in weight.
That's a great analogy because the methods we use rely entirely on that tiny weight difference. The text outlines methods like gaseous diffusion, where they turn the raw uranium into a highly corrosive gas.
Sounds dangerous already.
Oh, it is. Then they force it through a semi-permeable membrane. The slightly lighter U-235 gas molecules move through the microscopic pores just a tiny bit faster.
You'd have to do that over and over, right?
Thousands of times in a row just to get a noticeable difference. Another method is gas centrifuges. They spin the gas at supersonic speeds in massive cylinders, so the heavier U-238 gets pushed to the outside edge by centrifugal force.
And it takes so much raw material. The text notes that to get just 1 single kilogram of 5% enriched fuel for a civilian power plant, you have to start with 10 kilograms of natural uranium.
It's massively inefficient.
And if you are trying to build an atomic bomb, which requires over 90% enrichment, you need over 150 kilograms of natural rock to get 1 kilogram of weapons-grade material.
If we connect this to the bigger picture, this painstaking enrichment gap is exactly why we don't have to worry about a specific Hollywood nightmare.
Which one?
People often look at nuclear power plants and fear they could suddenly explode in a mushroom cloud like an atomic bomb.
Oh, right, like a nuclear blast in the suburbs.
Exactly. But scientifically, based on the physics we just discussed, it is physically impossible.
Wait, because of the fuel concentration?
Precisely. A civilian power plant is running on fuel that is only 3 to 5% enriched. A bomb requires fuel that is over 90% enriched.
So it just doesn't have the juice.
Right. The fuel inside a power reactor is simply too diluted. It is physically incapable of achieving the kind of runaway, instantaneous, perfectly timed chain reaction that causes a nuclear explosion.
Okay, so we've spent a fortune. We've built our massive centrifuge sandboxes. We've painstakingly enriched our uranium to 5%, and we've successfully started a chain reaction.
We have our fire.
Right, but how do we keep this reaction from just melting right through the Earth's crust? How do we tame this atomic fire and turn it into electricity you can actually use to charge your phone?
That takes us inside the reactor core itself. The engineering here is a masterclass in managing intense heat and controlling the flow of those splitting atoms.
Picture the core of the reactor. It is filled with thousands of what are called fuel rods. These are long, thin tubes made of incredibly durable metals like steel or zirconium.
And stacked inside them are little pellets of that enriched uranium.
And completely surrounding these rods is water, but not just a trickling hose.
No, this water is kept under immense pressure, up to 400 atmospheres.
400 atmospheres, that's insane.
Because the pressure is so incredibly high, the water can be heated by the reacting fuel rods to 450 degrees Celsius without boiling into steam.
It stays a liquid.
Exactly. This superheated, highly pressurized liquid water is then pumped through a heat exchanger.
Where it boils a completely separate secondary loop of water, creating massive amounts of steam.
Right.
And from there, the technology is actually incredibly old school. That high-pressure steam spins a giant, heavy turbine. The turbine spins an electrical generator, and boom, electricity goes out to the grid.
It's basically a really, really high-tech steam engine.
It really is. But it's a steam engine that requires some serious armor. Because that primary water loop is passing right by the nuclear reaction, the whole core is intensely radioactive.
Oh, massively.
It's shielded by layers of fire brick, steel, water, and up to 2 meters of solid, high-density concrete. That's all there to ensure no radiation escapes into the environment and to protect the workers operating the plant.
But there's a really weird detail in the source material about that highly pressurized water inside the core. It isn't just there to absorb heat.
Right. It acts as something called a moderator.
Yes, and this connects directly back to our miniature golf analogy. Remember how we said the neutrons coming out of a splitting uranium atom are moving way too fast to be caught by the next atom?
Yeah, they just skip right over the hole.
Exactly. So the water inside the reactor acts like a brake. The incredibly fast neutrons crash into the water molecules, lose a significant amount of their kinetic energy, and slow down just enough to efficiently split the next uranium-235 atom.
Wow, so the water literally moderates the speed of the reaction.
That's it. Without the water acting as a moderator, the fast neutrons would just escape, and the chain reaction would eventually sputter out and stop.
Which brings us to a really brilliant engineering loophole mentioned in our sources, the CANDU reactor.
Ah, yes. It stands for Canada Deuterium Uranium.
Right, because regular water, what nuclear engineers call light water, has a bit of a structural problem.
Yeah, while it does a great job slowing down neutrons, it also has a bad habit of absorbing a few of them. It acts like a very slight sponge.
And because it absorbs some of your precious neutrons, you are forced to use enriched uranium, that expensive 3 to 5% stuff, to make absolutely sure there are enough extra neutrons bouncing around to keep the fire burning.
But CANDU reactors don't use regular water. They use heavy water.
Heavy water. What makes it heavy?
This is water, where the hydrogen atoms are replaced by an isotope called deuterium. It's chemically the exact same as water. You could drink it, though we definitely shouldn't. But the deuterium atoms have an extra neutron in their nucleus.
So it's actually about 10% heavier than regular water?
Right, and that extra neutron changes everything. Because deuterium already has an extra neutron sitting in its nucleus, it doesn't want to absorb anymore.
The sponge is already full.
Exactly. It acts as a perfect moderator, slowing the flying neutrons down without soaking any of them up.
Wow.
Therefore, you don't need extra neutron-rich fuel to compensate for a leaky moderator. A CANDU reactor can run entirely on natural, unenriched uranium straight from the mine.
Okay, so what does this all mean? If heavy water lets you just skip that massive, incredibly expensive headache of the uranium centrifuges and enrichment facilities, why doesn't every single country just build CANDU reactors?
Well, because there's always a trade-off in engineering. You save a massive amount of money in infrastructure by avoiding uranium enrichment. But heavy water is incredibly expensive to acquire. It has to be manufactured and concentrated through its own complex, multi-stage chemical process.
Oh, so you're basically choosing where you want to spend your billions.
Mhm.
Do you want to pay to enrich the fuel, or do you want to pay to enrich the water?
Exactly. Pick your poison.
That makes sense. It is incredible how many ingenious ways we've figured out to harness this. We've designed a machine capable of generating limitless, carbon-free power.
We have.
But if we're being honest, and as our sources heavily detail, playing with the fundamental forces of the universe carrying profound existential risks.
We absolutely have to acknowledge the hazards. When you are dealing with a fire that doesn't need oxygen, a fire that burns from the inside out at the atomic level, losing control of the heat is catastrophic.
The text outlines exactly what happens if those pressurized cooling systems fail. If the water pumps stop and the temperature in the core reaches 1200 degrees Celsius, the intense heat actually causes the water molecules to physically rip apart into raw oxygen and hydrogen gas.
And hydrogen gas is highly explosive.
Right. This isn't theoretical either. This is exactly what caused the devastating explosions at the Fukushima plant in Japan after the tsunami. The hydrogen built up and ignited.
And if the temperature isn't controlled and keeps climbing, if it reaches 2200 degrees Celsius,
What happens then?
the zirconium and steel fuel rods themselves begin to literally melt into a liquid radioactive slag, burning right through the containment floor.
A full core meltdown.
Yes, that's the terrifying scenario we saw play out at Chernobyl.
And even when the reactor works perfectly for decades, you are still left with the waste. After the uranium has spent years in the reactor, it is intensely radioactive.
Oh, incredibly so.
The text notes that the spent fuel has to be pulled out by remote cranes and kept submerged in giant pools of water for decades just to let the immediate decay, heat, and intense radiation die down.
And that's just step one.
Right. Eventually, it has to be buried deep underground, encased in glass and concrete in stable geological layers, because it will remain highly dangerous to human biology for thousands of years.
It is a massive generational burden, but that burden makes a dark kind of sense when you look back at the historical origins of this technology. The peaceful, carbon-free power grid was never the primary goal.
No, it really wasn't. The history section of our source text reads like a geopolitical thriller, but it's completely real. It starts in 1934 when German scientists first discovered that atomic fission is actually possible in a laboratory setting.
And immediately the global scientific community realizes what this means. A massive, unprecedented release of energy.
By 1939, the geopolitical situation in Europe is deteriorating rapidly into World War II. And Albert Einstein, who was a German-born Jewish scientist who had fled the Nazi regime, writes a desperate letter to U.S. President Franklin D. Roosevelt.
A letter that changed everything.
He warns the president that the Nazis have suddenly stopped selling uranium from the mines they've conquered in Czechoslovakia.
Which is a huge red flag.
A huge red flag. He warns that the German military could be using this new physics to build a bomb of unimaginable destructive power.
And that letter changed the entire course of human history. The United States government, terrified and determined to beat the Nazis to this technology at any cost, launched the Manhattan Project.
They poured over $2 billion into it, an astronomical sum at the time. They needed absolute airtight secrecy, so they chose a desolate, punishing stretch of desert in New Mexico to build a secret city.
The area was historically known by Spanish explorers as Jornada del Muerto.
The journey of death.
Yeah, you literally can't make that up.
And there, isolated from the world, thousands of the brightest minds on Earth worked feverishly on turning Einstein's math into a weapon. The tension was unbelievable.
They didn't even know for sure if the chain reaction would stop.
Right. One prominent scientist reportedly took bets on whether the explosion would ignite the atmosphere and destroy the entire state of New Mexico.
But they proceeded anyway. And on July 16, 1935, at 5:30 in the morning, they conducted the Trinity test.
The sensory details in the text are haunting. A flash of light that was visibly brighter than the midday sun. The iconic, terrifying mushroom cloud violently expanding into the dawn sky.
And the heat of the blast was so utterly intense that the desert sand at the detonation site didn't just burn.
It melted, right?
It was instantly melted and fused into a radioactive, jagged green glass. And the shockwave was felt and heard 150 miles away.
Less than a month later, President Truman made the fateful decision to use the weapon in a theater of war.
Yeah.
On August 6, 1945, a B-29 bomber called the Enola Gay dropped the uranium bomb over the Japanese city of Hiroshima, detonating it 580 meters above the ground to maximize the blast radius.
The devastation was absolute. It was the largest single massacre in human history, wiping out a city in a matter of seconds.
Which raises an important question, perhaps the most important question of the modern scientific era, about the dual nature of discovery. The exact same physics, literally the exact same atomic mechanisms of uranium-235 absorbing a slow neutron, splitting apart, and releasing binding energy that offer humanity carbon-free, limitless electricity.
And were birthed solely to create the most devastating weapon ever conceived.
It's a deeply sobering reality. The same glitch in the math that powers modern cities today is the exact same glitch that leveled them in the past.
And we can't unlearn the science. The physics simply exists. We just have to choose, generation after generation, how we apply it.
Wow. Well, we've journeyed all the way from Albert Einstein's chalkboard, where the concept of missing mass was first theorized to be energy, through the colossal high-pressure engineering of modern light water and CANDU reactors, to the searing desert sands of the Manhattan Project.
It is an immense amount to take in. The sheer scale of the energy, the microscopic precision required to harness it, and the heavy responsibility of wielding it.
But I want to leave you, our listener, with a final provocative thought, something to ponder as you go about your day.
What's that?
Everything we've discussed, the massive cooling towers, the uranium centrifuges, the radioactive waste, the bombs, all of it relies on fission. The violent splitting apart of heavy, unstable atoms.
Right.
But right now, scientists all over the world are racing to master the exact opposite process. Fusion.
Fusion.
Yeah, this is the process that powers the sun and the stars, where incredibly light, safe atoms like hydrogen are forced to combine, releasing even more energy than fission.
It's the holy grail of energy.
Imagine a future where we unlock the immense power of E=mc² without the risk of meltdowns, without the threat of weapons-grade enrichment, and without leaving centuries of radioactive waste for our descendants to bury.
That would change everything.
We spent the entire 20th century mastering how to violently split the atom. Perhaps the next great human adventure is learning how to safely put it back together.
It's an incredibly hopeful vision for the future. And remarkably, it relies on exactly the same foundational understanding of mass and energy we've explored today.
So the next time you pick up a rock and you feel its weight in your hand, don't just see a dull piece of the earth. Think about the binding energy. Think about the invisible cosmic glue holding its universe together, and remember the sleeping giant inside.